Hi guys. I told you that I was either going to wait until Monday to try to do the rest of these videos. However, I've decided that I'm sitting here at Starbucks. It's such a nice day. It's in the morning. I'm going to finish them now. You have to bear with me. If the music's too loud, I'm really sorry. Also, I don't have a board or anything that I can really show you anything, so I just have some pieces of paper out, so you're just going to have to bear with me for that too. I want to review a little bit on the videos that I've done earlier about the same chapter, so still chapter 27. So let's kind of review just a few things. Now we talked about a guy named Max Planck, and we knew that there was a big problem at the end of the 1800s where scientists said that they weren't able to understand why there wasn't always a continuous spectrum, and why we sometimes see dark bands and then random colored bands and things like that. Planck said that because energy is quantized, we can see not just a continuous spectrum. So Planck is the one who really started this quantum of energy thing. And a quantum just means, again, that little specific amount of energy. So quantum just means that there's a discrete or a very certain, very specific amount. Okay? Planck came up with a formula to calculate the energy of an electron, or the amount of energy that an electron will absorb, or the amount of energy that an electron will emit. So that formula was E equals N times H times F. Now what does the N stand for? N stands for energy level. So the N is just going to stand for that energy level. And remember, when we talked about energy levels in that last one, we know that the energy level of the atom is just whatever row it's on that periodic table. So energy level just corresponds to the rows of the periodic table. We also talked about that when we move farther away from the nucleus, that we're going to need more energy. But why is that? It's because there's going to be a weaker attraction, and electrons want to be closer to a positively charged nucleus. So because there's a positively charged nucleus and there are negative electrons, they want to be attracted to one another. And what tells us that? The law of charges. Opposites attract, like charges will repel. So as the electron gets farther away from the nucleus, I have to add energy to it, because it's literally like I'm having to pull that electron away from something that it wants to be around. Think about a little kid who is starting school for the first time, and they absolutely do not want to leave their mom and dad, and the kid is just attached to their parents at the leg, and they are not going to leave. And it's going to take a lot of energy to try to pull them off of their parents to get them into that classroom. There's a good analogy. Okay, so again, Planck had this formula, E equals N times H times F. N stands for the energy level. H stands for Planck's constant, and that number will always be 6.63 times 10 to the negative 34th. And you will always be able to find that where? In the front of your test book. And that will be true for the free response. That will also be true for your multiple choice questions. So you're always going to be able to find that in the front of your test book, okay? Finally, the F stands for frequency. And we know that frequency is measured in per seconds or in hertz, okay? So that was Planck's formula for finding the amount of energy that an electron has. We talked about how Einstein then came along. And Einstein said that electrons aren't able to just absorb energy, but they're also able to emit that energy. So just like you can get really, really, really excited about something that you really want to do after school, you're absorbing in all that energy, you're getting yourself pumped up. Once you go to that place, or once you do that thing, you're releasing that amount of energy, so you're emitting that energy. So Einstein said that not only am I able to absorb, I'm also able to emit energy. Now Einstein tweaked Planck's formula a little bit, and he kind of just dropped out that energy level. So Einstein says that the energy can be found by just taking h times f. And we know h is just Planck's constant, and it's always going to be the same number. It will always be that 6.63 times 10 to the negative 34th. And I can always find that in front of my test booklet. So if I'm given that, I can find the energy if I know the frequency. So Planck's constant times frequency, so h times f. That's what Einstein says. So really Einstein's trying to tell you that it doesn't matter the amounts of energy levels, because the amount of energy should be the same amount if an electron moves from the first energy level to the second energy level, or from the second energy level down to the first energy level. Now, Einstein also came up with a photoelectric effect, and I think this was one of the last things that we were talking about in the last videos. Einstein said, or believed, that light can behave like particles and not so much like waves. And also, guys, just so you know, I am right now looking at slide number 9 on your chapter 27 PowerPoint. So I'm on slide number 9. But Einstein says that there are certain materials that are very photosensitive, which just means that they're really great at absorbing light. And most of those surfaces are going to be metal surfaces. So most of them are metal surfaces. And what happens when light comes in and strikes the surface, so when light's coming in and it strikes the surface, then I have these little tiny streams of electrons that are going to be emitted from that surface. So light comes in, hits the surface, little tiny streams of electrons are coming off of that surface. So that's what he calls a photosensitive material, that when light strikes it, it can release some amounts of electrons. Now, if you'll look with me on the next slide, which is slide number 10, and we've seen this before because I had those videos up for you to watch maybe a month or two ago about the same stuff. So you've seen this, I think, before. But there's something that we use now, and it's called a photocell. And there are lots of really great real-world applications for photocells, but you have to look at this picture, guys, okay? Here's how it's going to work. There is light that is going to strike a photosensitive material. And that photosensitive material is what Einstein called the cathode. So light hits a photosensitive material, and that's going to be your cathode. Those electrons are then going to move toward the anode. As electrons start moving toward the anode, we get a circulation of current moving through the cell. So as electrons are moving, as electrons move toward the anode, I start to get some amount of current. And so then that's how they've created some type of photocell. Now, with this construction kind of this photocell, or with thinking of these photosensitive materials and how they can emit electrons, some scientists have found that the current that's produced by these electrons moving from the cathode to the anode can measure their kinetic energy. On the next slide, on slide number 11, I wrote a lot of stuff, so there's a lot of words there. But the only reason that I did was because it's something that I don't think that you've ever heard about before, so I wanted to try to be as detailed as possible. So let's look at slide number 11. It says, with a positive voltage, the electrons are attracted to the anode, and all the electrons will reach it. So when there's a positive voltage, I have a light that hits that photosensitive material, and then electrons have to come off of it. And those electrons are moving from the cathode to the anode. So as they're moving to the anode, the electrons want to move to that anode. They want to go there. And that's because there's a positive voltage that's just allowing that flow to occur naturally. Now, scientists had found that if they reversed the voltage, if they made the voltage negative instead of keeping a positive voltage, that the electrons will then be repelled from the anode, and then they could calculate how fast those electrons were moving. So this is just something that they observed, and then they saw that electrons would move really, really far away from the anode. They did not want to reach the anode at all. So scientists had called this a retarding voltage. Okay, so when we switch from a positive to a negative voltage, the electrons no longer want to move to the anode. They want to stay away from the anode. And this is called a retarding voltage. As the retarding voltage becomes more and more negative, at some point, the electrons will never reach the anode because there's too much repulsion. So these negative charges are trying to get to something, and there's just so much negative charge that they don't want to be around each other, right? Because negative charges and negative charges repel one another. So at some point, the electrons will no longer reach the anode. Once that happens, we know then that the current will be zero. And that's because if I don't have this nice cyclic effect, I have photosensitive material, I have light that hits a metal, a photosensitive material, and electrons are supposed to be popping off of that photosensitive material. If I don't have them getting to the anode, then I can't complete that circuit. It's kind of like opening up a switch where the anodes are no longer getting to, or the electrons are no longer getting to that anode, so I don't have a circuit anymore. So that means there could be no current. So when I get to a point where my retarding voltage is too much, that my current is zero, okay? When the current becomes zero, this is something that scientists have called the stopping potential, and it's abbreviated with the symbol V with a little subscript 0. So our stopping potential is just a little V0, okay? Let's see if I need to tell you anything else about that, guys. Okay, so at stopping potential, whenever current turns 0, again, all that means is that electrons are turning around before they ever reach the anode, because they don't ever want to reach that anode. And just think about it, because there's too much negative charge, they're all repelling one another, and so they're all going to turn around and move in the opposite way. On the next slide, on slide number 12, it says for a given material and wavelength, if we increase the intensity of light, we will increase the amount of current. So really what that means is that if we increase the intensity of light, so if I have more light that is shining down on a surface, so instead of just going like this, I have a really bright light coming in and hitting this surface, what that means is I'm just going to have more current, and that should make sense. If I shine a brighter light on a surface, I'm going to have more electrons that are coming off, which means then that I'm going to have more current that can run through like a photocell, so it can run through a circuit. So more intense light, I get more electrons moving around in a circuit, okay? Now there were some scientists that developed another equation, and it's to find the maximum amount of kinetic energy that an electron can have, or the maximum amount of kinetic energy that an electron will emit in these photocells. And that equation is given to you at the bottom of slide number 12.